Okay, so this is a question number 13 from exercise 1. The question says that electric field inside a sphere which carries a charge density proportional to the density from the center. So as you can see here, the volume charge density of a solid sphere, okay, which is defined as the density is alpha r. So first of all, that density, volume charge density, is a variable which calls non-uniform distribution. Okay, now we need to find the electric field at r distance. So what we'll do here, we'll as r is variable, so we'll take a spherical element of r radius, dr thickness. Okay, and we try to find the charge enclosed first. Okay, what is the charge is present on this sphere? Then we'll calculate the electric field due to this sphere. The charge enclosed dq equal to rho dv. Okay, that's what formula is. Okay, this is the spherical element. What is the volume of the spherical element? 4 pi r square dr, which you can remember. dq is equal to rho. What is rho? Alpha r dv 4 pi r square dr. Now to find that enclosed charge, so q is equal to, this is the q charge which is present on this entire spherical element. Alpha 4 pi constant r cube dr. Limit of this one is 0 to small r because we need to write the answer in terms of r. So alpha 4 pi, okay, r to the power 4 by 4, and we'll put the limit 0 to r, so we'll get this one. So 4 cancel, so alpha q is equal to alpha pi r to the power 4. So this is the charge, okay, which is enclosed by this spherical element of radius small r. And we put the limit 0 to r only. So what is the charge present from 0 to r, which within the sphere. Now if the sphere has charge q, radius is r, so what is the electric field on its surface? So electric field is kq by r square. So E is equal to k is 1 by 4 pi epsilon naught into q is alpha pi r to the power 4 divided by r square. 4 pi cancel here, r square is cancelled, so what is electric field? Alpha r square by 4 epsilon naught. So this is the option B is correct. Okay, so hope you understood. Let's move to the next question. Okay, next question again 27 from exercise 1. The non-conducting sphere of radius r is filled with uniform volume charge density minus rho. So again it is a electric field due to a solid sphere. Okay, first of all we should know the formula of solid sphere inside, formula of electric field inside a solid sphere. So if it is solid sphere, okay, non-conducting, and this distance is r, so what is electric field at r distance? So E is equal to rho r by 3 epsilon naught. There is a standard formula. Now we are going to find the field at point P, any point P having position vector r vector inside the sphere. Okay, so in the diagram if we see, so this is the center here, C, and let's say this one is CP, and let's call this one as CP. So what is the electric field due to this solid sphere? Okay, so we can write rho by 3 epsilon naught, and what is that r vector? CP vector, yes or no? From the center only we take this r, na? Now we need to write this CP vector in terms of r and d. So for that you can see there's a there's a triangle, okay, vectors law of addition which you need to use here. This is d vector, this is CP vector, this is r vector. So you can see these two are in same order. So d vector plus CP vector equal to r vector. So CP vector is equal to, so that will substitute here. So electric field is rho, okay, rho is minus, so minus sign laga de, by 3 epsilon naught. CP vector is r minus d vector, and if you take minus sign into the bracket, so rho by 3 epsilon naught d vector minus r vector. So option 3 is the answer here again. So that's it. Hope you understood this question. Let's move to the next question. Okay, this question is related to the circular ring. Okay, we need to find the tension in the ring. Okay, so the thing is like this is a thin ring which has a charge q, okay, it is like present everywhere, and there's a small q charge present at the center. So now there will be a repulsion everywhere, okay, between this q and this one. So everywhere there is a repulsion. So each and every point charge on this ring will experience a repulsion from the q charge. So what happens? So because of this repulsion, the tension in this ring, okay, increases, okay, it becomes tight. So that's what we need to find. So to find the tension in this ring, what we will do here, we will take an element. So this is the element, a ring element, which I took as like symmetric about the y-axis. Okay, this ring element, let's say the charge is positive 1 and linear charge density is lambda, or can say the charge is dq. Okay, let's say this angle is theta, the theta angle आएगा, symmetric है. Okay, now there's a tension, so tension direction is always pulling. Okay, so if we draw the direction of tension, so it will be this one and this one. So tension direction, I hope you know from the 11th, always pull, sense आता है. Okay, now we'll take the component of tension here. So for that, first of all, this is theta, this will be one component and this will be another component. Okay, so this one is 90, okay, and this is 90 minus theta, that means this is theta. Okay, so this angle is theta here. So similarly this angle is also theta. So this component will be t cos theta. T cos theta, you can see these are cancelled. The other components t sin theta and t sin theta will be towards the center. So 2t sin theta, net force towards the center. Okay, and that will be, okay, there is a q charge placed here. So there will be repulsion between q and dq. And what is it? k q dq by r square. Okay, so this repulsion will be this side and this tension is this side and it is in equilibrium, so net force will be 0. So now let's just put the values to 2t. Okay, theta is small, so sin theta can be written as theta is equal to k q as it is, dq we can write as lambda into dl. Okay, the length of the element is dl, and dl we can write as, okay, I'll write here, dl is the length of r, which is r, sorry, radius is small r, okay, r into d 2 theta. Understood why I am taking 2 theta here? Because there is a 2 theta angle. ठीक है, तो dl की जगह r into d of 2 theta, या 1 second, sorry, no need to write d, okay, r into 2 theta, right, correct, yeah, r into 2 theta, right. This angle is theta, so no need to write d theta then. Okay, so I'll just put the values and we'll solve it. Theta cancel, 2 cancel, so tension is equal to, put the k value, 1 upon 4 pi epsilon naught into q into lambda will be the linear charge density of this ring, which can be written as q by 2 pi r into r. And there's one, I missed this one, r square is also there, so r square, so 1 r cancelled, or nothing is cancelled, so t is equal to q, capital Q by 8 pi square epsilon naught r square. This is the tension, and if we compare this with the given expression, so n value is 8. So that is the answer. So hope you understood. Thank you. Next, move to the next question. Okay, this question, let's see here. Spherical symmetric charge distribution is characterized by charge density having the following variation. Okay, this question is again like similar to the that one. Okay, that solid sphere and the volume charge density. Okay, so volume charge density is variable. Okay, given a different form. Okay, the process is gonna be same. Okay, I'll tell you. Okay, what we saw in the first question, the process is gonna be same, only that the expression is different. So what we'll do here, again at r distance, so I want you to try this question first, okay, just by taking the first question as a reference, and then you come back and check the answer. Okay, so this is again a spherical element we have, 4 pi r square dr. So enclosed charge dq is equal to rho into dv, right? So dq is equal to rho naught 1 minus r by r into 4 pi r square dr, limit, sorry, dq है, limit 0 to small r only. So q is equal to rho naught 4 pi r square minus r cube by r dr, limit 0 to r. The enclosed charge comes as rho naught 4 pi r cube by 3 minus r to the power 4 by 4r. So this is the what? Enclosed charge. Now once you know the enclosed charge, you can find the electric field is k q by r square. So E is equal to 1 by 4 pi epsilon naught. Q is rho naught 4 pi by r square, r cube by 3 minus r to the power 4 by 4r. Okay, 4 pi cancel, rho naught by 3, rho naught by epsilon naught r square will take into the bracket. Okay, according to the options. So it is r by 3 minus r square by 4. So this is the option D. Okay, so that's correct. That's it. Hope you understood. Oh, no, this is similar to the first question, right? Yeah. So let's move to the next question. With this question, again similar to the last question, the density is variable. Okay, but this time we have the material present between the shells. Okay, so this is gonna be a little different. So we have two shells A and B. Here we have material. Okay, so in this one we need to find the electric field. So process is same again at r distance. Okay, I'll take a spherical element of dr. So dq is equal to rho into dv. The charge enclosed, है ना? This charge enclosed we need to find. I'll just use a different pen. Wait a moment. Okay. So this charge we need to find, right? This one. Now this is the hollow part. Okay, this only charge we need to find. So rho is a by r and 4 pi r square dr. So q is equal to r cancelled, a into 4 pi r dr. Okay, what is the limit? Just pause it and think about the limit. Okay, the limit will be a to small r, because that red part, the enclosed charge, is between a and r. So q is equal to a 4 pi, it will be r square minus a square by 2. Okay, 2 get cancelled, so q is equal to a 2 pi r square minus a square. So this is the charge enclosed. Now we need to find the electric field. Okay, if you see the last line says the electric field in this region between the spheres will be constant, and there is a extra q charge particle present at the center. Now we'll write the net electric field between the region. So due to this enclosed charge, the electric field on its surface will be k q by r square, and due to this extra charge, k at r distance will be r k q by r square. है ना? तो at r distance point charge k q by r square, and due to this enclosed charge k q by r square, right? Now just put the value k by r square. Q is a into 2 pi r square minus a square plus k by r square into q. Yeah. अब this electric field is gonna be constant as per the question. So if it is constant, then that means dE by dr should be 0. So we'll differentiate here. So k a 2 pi. Just pause it and you try to differentiate this function. Okay, now that if you take this r square into the bracket, so 1 0 minus will be 2a square by r cube plus minus 2k cube by r cube, okay, is equal to 0. Now we can calculate k into 2 pi into 2a square by r cube is equal to 2k cube by r cube. This r cube cancelled, k cancelled, 2 cancelled. So you can see a value is q by 2 pi a square, and that is the answer, the option number 1. Clear? So just try to understand the concept above. Every time in the case of solid sphere, wherever that rho is a variable, I am using the same concept. D equal to rho dV, I am calculating the charge enclosed, then finding the electric field. Okay, so try these questions again and again until you feel confident on these type of questions. Okay, let's move to the next question now. Okay, so this question again similar. Okay, charge distributed with the sphere of radius r with the volume charge density rho a by r square e to the power minus 2 r by a, where a and r is constant. If the q is the total charge of this charge distributed, the radius r is. So charge enclosed you have to find, and then charge enclosed will be equal to capital Q, and then you need to find the capital R value. That's it. You don't need to find the electric field here. So I think you can do it. So just pause it here and you solve on your own, and then come back to see the answer. Okay, so here so I'll start with this one, dq to rho dv direct. Okay, the same thing is happening again and again. A by r square e to the power minus 2 r by a into dv. dv will be 4 pi r square dr. Okay, so now dq is equal to r square cancelled here, a 4 pi e to the power minus 2 r by a dr. Now what we'll do, we'll integrate from 0 to capital R, because we have to find the entire charge. So, and this integration dq will be equal to capital Q as per the question. So a 4 pi constant outside, integration of this one minus 2 r by a or minus 2 by a, 0 to r, put the limits, a 4 pi, just bit calculations, a by 2 e to the power minus 2 r by a minus e to the power 0, which makes it 1. Okay, then you can simplify it. What you can do is, you can, in next step you can take this minus sign to the bracket, so a and this one is cancelled. 2 pi a 1 minus e to the power minus 2 r by a. Okay, now take this side, so 1 minus e to the power minus 2 r by a is equal to q by 2 pi a, and exchange this one right side left side, e to the power minus 2 r by a 1 minus q by 2 pi a into a, then we take the log both sides, minus 2 r by a ln 1 minus q by 2 pi a into a. So now here capital R we need to find, so r is equal to minus a by 2 ln, and there's a minus sign, so we know, like according to ln property, it will be reversed, 1 upon 1 minus q by 2 pi a into a. So this is the answer. You check the options, so you'll find that the option 4 is the answer. Okay, the same thing again. Okay, let's move to the next question. Let's see this question. It is similar. It is again like based on the concept electric field inside the solid conductor. Consider uniform spherical charge distribution of radius r1 centered at the origin O. In this distribution, r2 is the radius of the cavity. OP is equal to A equal to r1 minus r2. If electric field inside the cavity at r is E. Okay. So again, the electric field inside this solid sphere. Okay. Electric field inside a solid sphere. How do we write? So let's say, so formula is E equal to rho r by 3 epsilon. Okay, now if I make a cavity here, okay, so let's try to understand this in a different example. Okay, so let's say if I make a cavity somewhere here. Okay, so if this cavity, okay, this is let's say O1, this let's say O2. Okay, and we need to find the electric field due to this solid sphere at O2. So first of all, I define the position of O2 here. So this is my O1, O2. Okay, so now okay, so here now the electric field due to this solid sphere, okay, at O2. So what will write? E electric field is equal to rho by 3 epsilon naught O1, O2. Okay, so that's what we will write. Okay, now electric field due to solid sphere at O2 is this one, plus electric field due to this cavity. Okay, cavity I can assume as a like density is minus rho. Okay, this is similar to the the center of mass concept. Okay, where we assume one density is positive, one density is negative. So I'll tell you one thing. What happened here, suppose this is a solid sphere of density rho, and there's a small solid sphere density minus rho. If I place this solid sphere, this one, somewhere in this, on this one, like here, so density rho of this bigger sphere will be cancelled by density of this sphere, yes or no? Rho minus rho becomes 0. Then density becomes 0, that means there is no charge present, so it becomes automatically a cavity. So I'm assuming that the density of this sphere, this one is minus rho, and this O2 is the center. So electric field at the center of a sphere is 0, right? So this is 0. So you can see here that net electric field at O2 is nothing but rho by 3 epsilon naught O1 O2. And according to the option, this O1 O2 is nothing but A vector. So you can see here the electric field depends only on A with magnitude and direction as well. So option D is the correct answer. Okay, so just remember, this is a very good concept here. Okay, so hope you understood. Let's move to the next question. Okay, let's see this question now. It is again related to the solid sphere, okay, where the density is constant and variable. A nuclear charge Ze is non-uniformly distributed within a nucleus of radius r. The charge density rho r is given by the graph. The electric field is only on the radial edge. Okay, the electric field at r equal to capital R. R equal to capital R. So this is our the nuclear charge. Okay, Ze. The total charge on this one is Ze. R equal to capital R means where are we? On the surface. So on the surface, I told, right, what is the electric field on the surface of a solid sphere? So we know, like, it is K Q by R square. And what is Q here? The total charge, which is K Ze by R square. So in this one, like, you can see here the electric field is independent of small a. Because, like, we are calculating the charge on the surface, that means we have to take the entire charge of the body. So within the body, how the density, how the distribution is, like, took place, that doesn't matter. Because in the end, like, we need to take the total charge, and total charge is nothing but Ze. If you want to calculate at a certain distance inside the sphere, then we see the variation. Getting my point here? So that the electric field is independent of A. So that option A is correct. Second is, for A equal to 0, the value of D, maximum value of rho, as shown in the figure. Okay, so for that we need to find the value of rho. Okay, the maximum value of rho as shown in the figure. Sure. So for A equal to 0, okay, when A equal to 0, so we'll write the equation of density now, the fourth question. You can see here there's a straight line. Okay, so we need to write the equation of density here. And then we'll integrate, okay, from 0 to r. Okay, so A value is 0 here, so we need to find the value of density, right? Okay, so in this one you can see here there's a straight line. So first we'll write the equation of the straight line. Rho r will be equal to, okay, this point is r comma 0, this point is a comma d. Okay, so we can write the equation of this one. So it will be coming straight line equation. What will write? Y minus 0 equal to minus d by r minus a into r minus r. Okay, we just simplified d by r minus a. So once again, this is r minus capital R. Okay, y minus y1 equal to m x minus x. So this equation I'm using if it passes through x1 comma y1. So this is equation straight line, right? So it is r minus r. So this is the, like, okay, here left hand side we have a density. Okay, so rho is equal to d by r minus a into r minus r, or a is given 0, so it is nothing but d by r, r minus r. Okay, now we'll calculate the charge. Okay, so dq is equal to rho dv. So rho is d by r, r minus r into dv, which is 4 pi r square dr. Now we'll integrate. So integration dq is the net charge, which is nothing but Ze is equal to d by r, 4 pi constant, and it is r square r minus r cube dr. limit 0 to capital R because A value is 0. Now we integrate it, ZE is equal to D by R 4 pi. It will come as R cube by 3. I'm putting the value limits, okay? You just integrate it, put the limits, and then you check. So I'm doing. So after like putting the limits, taking the LCM, you'll get R to the power 4 by 12. So 4 3 is 12, 1 R 1 R is cancelled, and D value we need to find because the charge is the total charge is ZE. So D value will be equal to 3ZE by what is it? Raw 4, yes, correct. Wait, something we missed here. There's no 4 pi R cube. Yeah. Okay, so fine. So option B is correct answer. Okay, so we are getting the option B. So that is the answer. Okay, now let's come to the fifth part. Fifth part, it says that the electric field within the nucleus generally observed to be linearly dependent on R. Okay, in this one, like we can take the like solid sphere, okay, for a reference. Okay, if you remember the formula of electric field inside a solid sphere when the rho is constant. So what is that formula? Electric field is rho R by 3 epsilon naught. So you can see here when rho is constant, then only E is directly proportional to R. So they are asking the reverse condition. If E is directly proportional to R, so what should be the rho value? So it should be constant. So the value of A should be tends to capital R, means from 0 to capital R, that rho must be constant. That's why the option C is correct. Okay, so hope you understood this question. Let's move to the next question. Okay, this question, two infinite planes which with uniform surface charge density plus sigma are kept in such a way that the angle between them is... Okay, these are the infinite sheets. We know the electric field due to infinite sheets, if it is plus sigma, the electric field at any point is given by sigma by 2 epsilon 1. So that's we are going to use here. So there are two sheets inclined at an angle of 30 degree. This is plus sigma, this is plus sigma. So this is the point, let's say. So this sheet will produce electric field in this direction, sigma by 2 epsilon naught. This sheet will produce electric field in this direction, sigma by 2 epsilon naught. Now we just need to resolve them. This angle is 30, so this 30, so this is 60. Okay, that's it. Now we can see here that if we resolve the component, so this is sigma by 2 epsilon naught, this is sigma by 2 epsilon naught cos 60, and this is sigma by 2 epsilon naught sin 60. Okay, now do this vector addition. So electric field is equal to sigma by 2 epsilon naught j cap. We'll write y cap as per the question options, plus sigma by 2 epsilon naught cos 60 1 by 2 minus x cap, plus sigma by 2 epsilon naught sin 60 root 3 by 2 minus y cap. Now we'll just arrange them. So sigma by 2 epsilon naught common, it is coming as 1 minus root 3 by 2 y cap minus x cap by 2. Okay, so that's the answer. Option 2 is correct. Hope you understood. So with this one, like I discussed some of the important questions from this electrostatics chapter. Hope these questions help you to solve the questions, to understand the concept. Thank you.